Hi, Chem 201. We are going to get into the meat of organic chemistry right now, which is actually looking at reactions and looking at reaction mechanisms. Organic chemists focus on reactions to a large extent. Um, Organic synthesis is one of the classic areas of organic chemistry. It's what I did when I worked for Johnson & Johnson for many years in drug discovery. Basically, you need to design, you have a molecule and then you need to design how you're going to make that molecule. And in order to do that, you also have to understand how these reactions work in terms of what is the mechanism, because with the mechanism, I can predict if two different products are able to form, which one would form preferentially. There's so many different ways that I can control what happens in a reaction if I understand how and why things are happening. So we're going to use our arrow pushing that we've used in resonance a lot in this section. So without any further ado, let's get to this. I'm going to share my screen and we're going to start on chapter 5, looking at the reactions of alkenes and alkynes. So again, this is our first introduction to real organic chemistry reactions. We've looked at acid-base reactions, and those are really important. Hopefully you guys did that activity in the last chapter, which allowed you to predict the products of various acid-base reactions. And now we're going to extend our knowledge and we're going to look at the functional group of a double bond and a triple bond and see what types of reactions those functionalities actually undergo. Now, first, we're going to look at the various types of organic reactions in general. Alkenes and alkynes tend to undergo an addition reaction, which is basically exactly what it says. I have some substance, X bonded to Y, that adds to the multiple bond of my unsaturated reactant, which can be the alkene or the alkyne. And what happens then is that I get a saturated product that only has single bonds. So here's my alkene. And basically, this double bond is actually going to be the reactive center in that alkene. My X is going to end up on one of those carbons of the double bond. And then my Y is going to end up on the other carbon of the double bond. So notice I went from a carbon-carbon double bond to two carbon something, a CX and a CY single bonds. This is fully saturated because these are sp3 carbons, which are tetrahedral. And this is what I call an addition reaction. Now notice I have two centers of reactivity. I have two pi bonds, right? These are the pi bonds that are reacting. And if I have two molecules of my X bonded to Y reagent, I can actually do two additions. You can imagine that sort of intermediate to this. I have an X and a Y. That would be one addition. And then just like the one above, I would have a second addition. And then I end up with, again, sp3 carbons, which are fully saturated. But now I've added 2 X's and 2 Y's to the carbons that were in my original alkyne. There's another type of reaction that we're going to cover in a little bit called an elimination reaction. And this is where I have a saturated reactant that yields an unsaturated product. And this is eliminating or losing groups from 2 adjacent atoms. This is literally the reverse of what we just did. This is a saturated carbon-carbon compound. And what I get is an unsaturated double bond. And I also get XY. This could be water, this could be HX, this could be a whole bunch of different types of reagents, this XY that is eliminated. So we're going to look at that. These types of reactions are going to be studied very in depth in chapter 7. The addition reactions are what we're going to deal with in this chapter, chapter 5. The next type of reaction is a substitution reaction. And this is a general reaction type where some atom or group of atoms is replaced by another atom or group of atoms. So if I look at it this way, if I have AB plus C, the B and the C actually switch and I get AC plus B. So my C substitutes for B in the original compound. This is also something that we're going to look at in terms of chapter 7. Substitution reactions and elimination reactions are the focus of that chapter. Here's an example. Here I have a carbon-chlorine bond, and here I have this alkoxide, and I'm replacing the chlorine with this OCH3. So this OCH3 is going to replace the chlorine. And that's how I end up with my product. This is a really versatile reaction. We can introduce a ton of different functional groups using this methodology. And again, we will cover this in a lot of detail in chapter 7, which is the next chapter after this chapter 5. And then finally, I have a rearrangement reaction. And this is where a molecule actually undergoes bond reorganization. And what I'm going to get is some isomer of my original compound. So this really, we're going to think about in terms of carbocation rearrangements in a little while. But notice if I have this carbon attached to this X attached to this Y, and now I have a double bond attached to the X, and this Y is attached to the C. This is a rearrangement where I have to sort of break bonds and rearrange atoms. And one example of this would be this isomerization from cis to trans. Remember, I actually have to break this double bond in order to rotate. I know that trans is more stable than cis. So if I do treat a cis alkene with acid, which actually forms a carbocation, then it will rearrange, and then when I get the final product, those two groups will be trans to one another because that's sterically, energetically more favorable. Now, this meeting this criteria, I'm just going to rearrange atoms when I have this rearrangement reaction. So most of the reactions of carbon-carbon multiple bonds are addition reactions, which is our focus for this chapter. And basically, again, I have some generalized reagent XY that adds to this multiple bond. Now, this XY can be water, it can be HCl, it can be halogens, it can be a lot of different substances. We're going to go over several types of addition reactions. One of these two bonds break, it's the pi bond, that's reactive. And then this single bond breaks, and then I have these new bonds that are going to form in that product. And basically I added X and I added Y to the two carbons of the double bond, which is this addition reaction. So here's a chart from our book. Again, look at these different reagents. My reagents are these XYs. So I have HX, I have H2O, I have XX, I'm going to have HBH2, and I'm going to have HH. And when I look at this, notice I'm adding these different combinations of the X and the Y across the double bond. If I add hydrogen and a halogen, I get a hydrohalogenation reaction. If I add water, which is H and an OH, I'm going to call that a hydration. This would be halogenation. If I add bromine, it's a bromination. If I add iodine, it's an iodination. If I add chlorine, it's a chlorination. Hydroboration is an intermediate where I actually go on and I form an alcohol. And then this reduction or hydrogenation is where I add two hydrogens and I go from an alkene to an alkane because I'm adding those hydrogens, which I'm not adding other functional groups. Here I'll get an alkyl halide, here I'll get an alcohol, here I'll get a dihalide, here I get this borate, and then I ultimately go to an alcohol. Now, another thing that we're going to focus on in terms of these reactions are categorizing these reactions by looking at energy diagrams for the reactions. A lot of you guys have had this material, especially, again, this is one area where if you took Chem 101 or Chem 110, you probably have an advantage over other people, because typically you don't get into this material until you take Chem 2 as well. So we're actually going to look at a graph of the energy changes that occurred during a chemical reaction. So my energy is on my y-axis, and the progress of the reaction, which is called the reaction coordinate, is on the x-axis. So this is an example where I have C plus AB reacting to form Ca plus B. So this would be considered a one-step reaction because I have one transition state that's actually formed. My products are lower in energy than my reactants, so this is exothermic. And we're going to learn about all of these different pieces of this energy diagram. This is where the energy of my reactants, my starting materials is. This is where the energy of the products are. The difference in the energy of the reactants and the products is my heat of reaction, or my delta H. And if my products are higher in energy than my reactants, that would be endothermic. And if they're lower, that would be exothermic. And we'll talk about that a little bit more. This is the transition state, which shows me how bonds, I have this partial bond that's formed. This bond is partially broken. This is showing exactly what's happening as I go from AB to CA. My C is coming in and forming this bond. My AB bond is breaking. So my transition state is always an energy maximum. And if I have more than one transition state, I have more than one step. So we're going to look at all of these different features. This, which is the difference between the reactants to the transition state, this is that energy barrier that needs to be overcome for the reaction to occur. And this is called the activation energy, and it's designated by E sub A. So let's look at these all a little bit more carefully. In my transition state, which is my energy maximum, right? It's a maximum on the energy diagram. I have an unstable species of maximum energy that is formed during the course of a reaction. My activation energy, E sub A, is the difference in energy between the reactants and the transition state. So this is the barrier. This activation energy is the barrier that I have to overcome with collision energy in order to have the reaction proceed. Various reactions that we're going to talk about all give different transition states. And characterization of the transition state is also a feature of trying to figure out what kind of reaction mechanism is actually happening in any given reaction. My energy of activation actually determines the rate of reaction. If this is very, very large, very few molecular collisions will occur with sufficient energy to reach the transition state, so the reaction is going to be slow. If this energy of activation is small, many collisions will generate sufficient energy to react and reach the transition state. So then I have a fast reaction. So I can judge the height of the hill that the reaction has to go through is going to be in a way I can predict the rate of the reaction. If that hill is really large, the reaction will be slow, and if that hill is smaller, the reaction will be faster. I also have this heat of reaction, or my delta H. If you've had any thermodynamics, this is also called enthalpy. And this is the difference in energy between the reactants and the products. In an exothermic reaction, the energy of the products is lower than the energy of the reactants, and heat is actually released, or heat is liberated. That means if I were monitoring this reaction, heat is generated, my temperature would tend to increase in the lab setting. If I have something that is endothermic, here my reaction has the features where the energy of the products is higher than the energy of the reactants. So here heat is absorbed, and if I were monitoring temperature, my temperature would actually go down and I would feel the reaction flask get cooler. I could monitor it with a thermometer in which my temperature would literally go down. Sometimes qualitatively, I can actually feel the outside of the flask and I notice that it's getting cooler. So here's an energy diagram for something that is two-step and exothermic. I notice it's two-step because I have two transition states. I have two energy maximum. This would be transition state 1. This is transition state 2. Here's my reactants. My products are lower in energy. So the difference between the reactants and the products is going to be that delta H. Heat is given off in this reaction, So this is going to be exothermic. I have two different activation energies. I have this hill, which is the activation energy for the first step, and then I have this hill, which is the activation energy for the second step. And this energy minimum is going to be this intermediate that's formed. So the intermediate is actually the product of step 1 and is the reactant of step 2. Step 1 has a much larger activation energy. So step 1 is called the rate determining step. The rate is always determined by the slow step. So the larger hill is going to indicate that that energy of activation is larger, and it's going to, the reaction overall is going to occur slower. Now my second reaction, my second step is reaction of the intermediate to form the products. That has a much lower energy of activation. So my first step is the bottleneck. That's the one, because of this large energy of activation, that sort of holds everything up. And that's why it's called the rate determining step. 2 can happen fast. As soon as the intermediate forms, it's going to basically go to the product. It's hard to get the intermediate to form because this energy of activation is so high that not many molecules will have that energy from colliding with each other that allows this reaction to proceed. So again, the rate is determined by the step that has the highest energy of activation, or is the slower step in the reaction sequence. I also have reaction intermediates in that 2 or 3 or 4 step process. That's going to be an energy minimum, and it's going to occur between 2 transition steps. These are very highly reactive materials, and very rarely can they be isolated. Usually I can get some evidence that they exist, but I can't isolate it. And I just know, based on the mechanism and kinetics experiments, what it may look like. The rate determining step is my slow step. So this is the reaction in that sequence that crosses the highest energy barrier. Is going to be the slowest step in the multi-step reaction. And again, if I characterize those steps using an energy diagram, it's going to be the reaction that has the highest barrier, the highest energy of activation for that step. Now, we are going to really focus on reaction mechanisms. This is a step-by-step description of how a reaction occurs. It's looking at which bonds break and which ones form. It's looking at the order of the steps and the bond breaking, the relative rates of the various bond breaking and bond forming steps. If the reaction takes place in solution, it looks at the role of the solvent. What does the solvent actually do? Does it help stabilize something? Is it facilitating the reaction in some way? If I have a catalyst, what is the role of the catalyst? And I'm looking at the energy of the entire system throughout the reaction, looking at those reaction energy diagrams. What the reaction mechanism is not is a list of reagents or experimental conditions. Those reagents and experimental conditions are either present as reactants or as conditions and things over the arrow. What they don't tell you is anything about how bonds are breaking and how bonds are forming. So I'm actually going to track my electrons. When a bond breaks, my electrons are going to be moving, and I'm going to use those arrows, those double-headed arrows, in order to track the movement of electrons just like we did with resonance, and just like we did when we started looking at how bonds were made and broken in those acid-base reactions. So to determine a reaction mechanism, I have to do a lot of experiments. I have to design those experiments so that they're going to reveal details of the reaction. And then I'm able to propose one or more sets of reaction steps that might account for the overall chemical transformation. There are still reactions that we really don't know exactly what happens when I have bond making and bond forming. But a mechanism does become established when it is shown to be consistent with every test that can be devised. That doesn't mean that this proposed mechanism is correct. All that means is up until now, that is the best explanation that I can devise for this particular reaction. So my reaction mechanism is using that symbolism of the curved arrow to show the redistribution of my valence electrons that occurs as covalent bonds are broken and new bonds are formed. The next several screens are going to show the most common patterns that occur in the reaction mechanisms that we present in this particular text. Sometimes I'm going to explain them the way they're explained in the text, and also maybe a little bit differently, because sometimes this text will maybe oversimplify things a little bit, but it'll become clear as I go through these explanations. This arrow pushing is extremely important in organic chemistry. In 201, I focus on it a significant amount. In organic 1 or organic 2, mechanisms are a huge part of understanding organic chemistry, because if I know the mechanism and I know the chemistry of what these compounds, these bonds are going to do, I don't have to memorize 250 reactions. I know based on what functional groups are present and my analysis of where the electrons are and if is it polar or non-polar, all this kind of stuff, and then I can figure out what's likely to happen next. This is a huge time saver for organic chemistry students, because understanding what happens is far superior of a method to learn reactions than trying to memorize a whole bunch of reactions that we go through. So my mechanism is my theoretical framework within which to organize my descriptive chemistry. There sincerely is an intellectual satisfaction that is derived from constructing these mechanisms, from constructing models that accurately reflect the behavior of chemical systems. When I was in grad school, we would have group meetings, and literally we would just do predict the product mechanisms, predict the product mechanisms. How does this reaction work? Where do the electrons go? How can I control it? What can I do with this reaction? So there really is an intellectual satisfaction. It may not be evident initially, because many people find that these reaction mechanisms can be fairly difficult in the beginning. But hopefully you'll be able to appreciate this power that you get when you actually understand what's happening in a given chemical reaction. So let's go over some of these common reaction mechanisms. The first one is going to be add a proton, right? So I'm adding an H+. That I have an acid, which is a proton donor, and I have a base that is a proton acceptor. I'm going to use those curved arrows in order to show how that proton transfer occurs. My curved arrows show the redistribution of those valence electrons, and I see how bonds are broken and how a new bond is formed when a proton is transferred from the acid to the base. So if I look here, right, here's my area of high electron density, my lone pair. And my arrow always originates at the area of high electron density. It's always going to be from a bond or some lone pair or non-bonded pair of electrons. Remember, this is partial negative and this is partial positive. This hydrogen is got low electron density because it is partially positive. So this lone pair is coming in, it's going to attach to the hydrogen. So I now form a bond between the nitrogen and the hydrogen. These two electrons in that oxygen-hydrogen bond are going to end up on the oxygen. This bond here is breaking. So in the final analysis, these are the electrons from that bond here that end up on the oxygen. And that gives it a negative charge because I have 7 electrons around that oxygen. I should have 6. And this is the new bond that is formed. And this is a positive charge because nitrogen is supposed to have 5, half the bonding is 4. That gives me a positive charge. So I have just added a proton to the nitrogen atom, and as a result of its non-bonding pair, that lone pair attacking that hydrogen and abstracting that hydrogen proton from the acid. So this is what you would have to write. You have to draw these curved arrows to explain any bond that is being broken and any bond that is being formed. And I typically will go stepwise. Sometimes this is the first step and now my products are going to react in some other way, or just one of the product is going to react in some other way. So this is pattern 1, which is adding a proton. This is another example of this add a proton reaction. Here I have an area of high electron density, which is the pi bond. These electrons in that pi bond, those electrons have an increased electron density because they are in that pi bond, which is a little bit farther away from the nuclei, right? That's that side-by-side overlap. That pi bond, those 2 electrons actually come across, and this is H3O plus. This hydrogen is the hydrogen that's being transferred. So these electrons are going on this oxygen. So I form a new bond between this hydrogen and the carbon. This leaves a positive charge on this carbon because now this electron, right, this bond here has one of those double bonds has broken. So now I have fewer electrons. I only have 3 groups bonded to the carbon because these electrons moved away from this carbon, and the bond is between this carbon and this hydrogen here. And that's what I see right there. So the electrons in this single bond were once part of that pi bond, and it abstracted the proton. Notice I get water when I abstract the proton from hydronium ion. That's neutral, where the whole hydronium ion was positive. And I end up with this carbocation, which is actually an intermediate. This carbocation will then go ahead and react further. The other interesting thing to remember is that this is called a nucleophile because it is electron poor and it wants electrons. This is actually, I had that wrong, sorry. The nucleophile is electron rich. So I either have a bond or a lone pair or a negative charge, and this is wanting a nucleus because that's positive charge. And then this is an electrophile, which is electron deficient, right? This oxygen is going to be positive, right? So this is usually a positive charge or a partial positive charge. Because it's partial positive or fully positive, it's electron deficient and it wants electrons, hence the electrophile. So this would be another step that indicates a different way where I follow this pattern of adding a proton. Now, while it's most accurate to show proton transfer with H3O+, because remember, as soon as H+ is formed, it's going to react with water, and basically what I form is H3O+. Organic chemists still indicate this proton as an H+ in reaction mechanism. So I'm often going to simplify that equation to show just the proton and the formation of my new covalent bond. So again, if I'm looking at this as my source of electrons, these electrons are going to come out and pick up the hydrogen. By using this, it's assumed that hydrogen is actually part of the H3O+. I try to give you the full mechanism as we go through a lot of these reactions so that you don't get that confused. But you're also going to see this H+ used a lot. And basically what I have is this new bond that's forming. And then because those electrons left this carbon of the double bond, that is electron deficient. It's going to be this carbocation intermediate that's going to form a bond with something else in another step. So this is another shortcut way of doing the reaction that we just did on the previous slide. Okay, now I'm in pattern 2, right? Which is take a proton away. So this is actually reversing pattern 1, where I end up taking a proton away instead of adding a proton. The mechanism for this is very similar to what we just learned, except now we're going to focus our attention on the compound that loses a proton instead of the compound that adds a proton. So in this example, I have my negative charge lone pair. Now this is the reverse of the previous reaction. So it really depends on your perspective on what the step in the mechanism is. But here, this is negative. This is a nucleophile. It's going to be electron rich, high electron density. So the base of my arrow starts there. This is positive, right? But this is a polar bond. So this is really very partial positive on that hydrogen because nitrogen is very electronegative. So this is coming around, attacking that hydrogen. These electrons in that bond are going to go on the nitrogen. So what I see is those electrons end up as this lone pair. I've taken a proton away and I formed this bond between the hydrogen and the oxygen. So that's where I get that OH. You need to be able to accurately draw these arrows. You always start the arrow. So I'm going to start the arrow at an area of high electron density. And I'm going to end the arrow at that area of low electron density. So remember, I go high to low. If you reverse those arrows, you are very, very, very wrong. And you will not get any credit. You have to pay attention to what's happening and how I use these arrows to effectively indicate what this reaction mechanism is. Here's another pattern where I have the reaction of an electrophile. Remember, this is partial positive or positive. It's electron poor or electron deficient. And then I react that with the nucleophile, which is going to be a lone pair or a bond or a negative charge. This is electron rich to form a new covalent bond. So here's my carbocation. This is a carbocation like I formed in those previous reactions. So this is electron deficient, right? This is the electrophilic carbon. So this chlorine is negatively charged. This is a nucleophile. I start at the area of high electron density. Remember, this is high electron density, and this is low electron density, that positive charge. So I start here, and I end up just adding those electrons and forming that new covalent bond. So this new covalent bond is formed with those electrons. Just to reiterate, my electrophile is electron poor, and it will accept a pair of electrons to form a new covalent bond. This can also be described, according to acid-base theory, as a Lewis acid. A nucleophile is electron rich. I can donate a pair of electrons. This would be my Lewis base. So this one can accept a pair, this can donate a pair. And again, that's what we talked about in Lewis acid and base theory. These words are important. You need to be able to use them when you describe something that's happening. Like you would say, chlorine ion is acting as that nucleophile. It's an electron-rich species that is attacking the carbon, the electrophilic carbon of the carbocation. And you want to be able to start interjecting this terminology into how you're describing things, because when you have those sorts of problems that you need to answer on tests and that kind of stuff, you want to make sure you use the correct terminology to get the most points. Now here's another pattern, which is what we're going to call rearrangement of a bond. This rearrangement occurs when I have the electrons of a sigma bond break the bond from one atom, right? I'm breaking the bond from one atom, and I'm forming a new covalent bond with an adjacent atom. This is a rearrangement of a carbocation. And we're going to talk about this a lot in the coming chapter. So notice these electrons here, let me use this red pen. These electrons here are going to shift over to the adjacent carbon, and I actually just hop that hydrogen over. I shift that hydrogen to the adjacent compound or the adjacent carbon. So now this carbon is attached to this hydrogen, but I took those electrons away from this carbon. So this carbon has a new, is the new positive center of the carbocation. Now, the driving force for this rearrangement is that this carbocation is more stable. So I increase the stability, I lower the energy by doing this hydride shift, and I form a new, more stable carbocation. So we're going to look at all of these different patterns in the context of how we do different reactions in the coming chapters. There's another pattern, which is basically breaking a bond. Oh, I want my yellow. Breaking a bond to form a stable molecule or ion. Now, this could also be considered loss of a leaving group. If I look at this particular reaction, these electrons, actually this entire bromine actually just leaves. This bond breaks, those electrons go on the bromine, they end up here, and I form this bromide ion. But what I get is a very stable carbocation. This is very stable as an intermediate. So when it does this, when I lose the group, this group is leaving, so it's called loss of a leaving group. That group will take the electrons from that former single bond with it. So this again is called the leaving group. The group that leaves is called the leaving group. And when this happens, when that bond breaks, I'm going to form stable ions or molecules, and it's the stability of those intermediate species that is going to allow this reaction to occur. At this point, we are going to stop. And next, when we come back, we're going to start looking at these reactions of alkenes and alkynes. You're going to learn how to predict the product. We're going to learn how to write reaction mechanisms. You do have to know these steps that we've just talked about, and you have to be able to look at the bonds that are breaking and the bonds that are forming in order to be effective at writing reaction mechanisms, which is a very important skill in this class. So practice makes perfect, and it's always good to reinforce your learning with practicing. If you need any help finding practice problems, let me know, and I'm sure I can suggest something for you. That's going to actually stop this or end this particular part of the lecture. And then next time we get together, we're going to start talking about the actual addition reactions of alkenes in a lot more detail. So have a good evening.